着手したのがですね、先ほどの田中准教授からご紹介をしたソーラーキオスクにつながっているというふうに考えております。また本年度のですね、TICAD にも私ども展示をすることができましたけれども、そういったことにつきましてもですね、課長から応援をいただいているということでございます。引き続きよろしくお願いいたします。で、関係者への期待、講演者の最後になりましたけれども、最後に、米国電力研究所EPRIバイスプレジデント、電力の送配電や利用を担当されている部門の責任者でございますけれども、マーク・グラナン博士からお話をいただきたいと思います。EPRIにおきましてはですね、先ほどもご紹介しましたように、私どものルーターの実証実験を共同でさせていただいている関係でございます。それでは、ドクターマーク・マクグラナン、フロア is yours, please.
Thank you very much. I want to thank the organizers of this workshop for inviting me. Professor Abe-san and I were here 1 year ago when this facility was just being finished, wasn't done yet, and we said it would be a very good idea to have a workshop here. And now I'm invited, so I'm very lucky. Just my background, I'm the Vice President for the Power Delivery and Utilization Research Sector at EPRI. That's the part of EPRI that does research on everything from the generator to the washing machine. So everything in between is part of the power delivery and utilization sector. It's where we do our smart grid research, and it's a very exciting time. And listening to the speakers that we've had so far today, it's very exciting to see that the challenges that we have in the smart grid are the same all over the world. So it's a very great opportunity for collaboration. Let's see. Use this one. Okay. What I want to do is give you a very brief introduction to the Electric Power Research Institute, if you're not familiar with EPRI. And then we'll focus on the challenges and the roadmap for working on the smart grid. And I think we'll see some of the same challenges that we've already heard today. So it'll be reinforcing some of the issues that we need to work on together. Then I'll describe the approach of using demonstrations to help address some of these challenges and some of the demonstrations that we're working on. And we'll finish up with a few comments on how I think that the digital grid concept fits into some of these challenges also. So hopefully that will be useful as we go forward. At EPRI, we have a mission description that is very simple. We're a research organization that is made up of utility members from around the world. Our funding comes from electric utilities from around the world. We're the research organization for those utilities. We're a nonprofit research organization, so we have a mission a public benefit mission to improve the electric supply system. And we do that by working on research that helps the electric supply be more reliable, more affordable, which is not always the same, and environmentally responsible. So trying to balance those objectives all the time. The research area that I'm responsible for is divided into these 4 research sectors: transmission, distribution, the energy utilization, and now we've created a 4th research area around the information and communication technologies. That area cuts across all the other 3 areas, but we try to align the research areas with the organizations of our member utilities. And usually our utilities have separate parts of the company that works on the ICT problems. So it makes sense for us to have a separate research area that works on those problems in cooperation with the other three areas. And we use, the size of our research area, the power delivery and utilization, is about $100 million per year. We have, and we have about 100 utility members that provide that funding for us. I have three objectives that I try to emphasize every time that I'm talking about our research. And the first one, and the one that is kind of includes all three, is collaboration. So it's a great opportunity for me to be here and collaborating with NIDO and TEPCO and NEC and other Japanese technology providers and the Digital Grid Consortium. It's very exciting to include that in those organizations in our research collaboration. But the research that we work on is research that fits into this collaborative model. We don't do too much one-on-one research. We try to solve problems that utilities are happy to work on together because they all have the same problem, especially at a time when budgets are tight and it's difficult for utilities to fund research to do themselves. It's much more efficient to contribute to a collaborative effort and everyone benefit from the research results. And as part of that collaboration, we have to make sure that we coordinate with industry organizations like CGRE and IEC and the Department of Energy in the US and many other organizations to share the research results and achieve our public benefit mission. As part of that mission, international coordination is also very important. We get the value for our US members by including many international utilities in the collaboration because we get a lot of different perspectives besides just the increased collaboration from a funding point of view to accomplish the research. So the international cooperation is very important. As we look at the development of a roadmap for the smart grid, you have to start with a vision of where you want to go. A roadmap process is to look at where you need to get to and look at the gaps that exist in achieving that vision. So the roadmap always starts with a vision. This slide kind of illustrates that vision, and it's very, very similar to the vision that we saw earlier that NIDO presented, the vision slide. It's the same kind of challenges when we look at this vision that we're going to run into. Integrating widespread renewable resources and distributed generation, integrating bulk renewables to the transmission system and developing the infrastructure to support that, building a communication infrastructure that can connect all of these resources and make them work together, new control systems to integrate all of these resources, and making the customer part of that operation of the grid, the customer with their renewables and their energy storage devices and their loads that are flexible and can be part of the operation of the grid. So it's a different model than the power system that we have now, and there's a lot of challenges in achieving that. So I thought that would be useful to just look at some of the categories of these challenges in achieving that vision. One of the important challenges right to start off is to look at the architecture requirements for that grid. There's many more stakeholders and organizations that are part of that vision than one utility that manages everything. Now we have aggregators and we have customers with resources themselves, and we have companies that are developing financing and leasing models for generation resources on the grid and storage resources on the grid. We have infrastructures for electric vehicle charging with third parties completely managing those resources and the use of that electricity and maybe offering those resources to the grid as a resource as well. So there's many more stakeholders, and we have to make sure that we have an architecture that can handle all of the information flows that are associated with all those different stakeholders. Information is one of the key aspects of the smart grid. Sensors, monitoring, and all of the data associated with the smart grid that pose very unique challenges in managing all of that data. I think it's particularly important to look at the control system architecture for the smart grid. We call it a distributed controls type of architecture where we have to integrate many different independent control systems instead of having one central control that controls everything. We use the term localized energy optimization for control systems that would operate locally in a home. You use the term here, home energy management systems, the HEMS, or the building energy management systems, the BEMS. Those systems are local control systems that we have to understand how they operate if we're going to manage the grid. And we have to have models for those control systems. So we have new modeling challenges to plan the future grid, including representations for things like consumer behavior now has to become part of the model of how we plan the system in the future, because we don't know what capacity we're going to need unless we can predict how these control systems will behave. It's a very special challenge. And these modeling challenges have to work both for planning the future system and for managing the system right now in the real time. So the modeling challenges are particularly important. A theme that we've heard throughout the afternoon today is the integration of all of these distributed resources as a challenge that's facing us right now. When we look at Germany and Italy and Spain and California and Hawaii and now Japan, in the same situation. Very high penetration of renewables and getting higher all the time. Distribution systems that are not capable to integrate all of that photovoltaic resource, and customers that want to be part of managing the grid and want to operate more efficiently. Energy storage that's still expensive, but obviously part of the solution. Electric vehicles that could be part of the solution or could be part of the problem, that we have to integrate all of these technologies and optimize the way the grid works with all of those. And there's many different, each one of these technologies that's part of the problem is also part of the solution. So when we look at customers' loads, now that they can contribute to the flexibility of the grid because we can manage them with the home energy management system and just not use loads that are not required right now if the electricity is very expensive or we're in a situation where we need to reduce load. We can take advantage of distributed energy storage. We have tested the NEC storage device in our labs in Knoxville, along with many other storage devices. That particular picture is the American Electric Power experiment with distributed energy storage at distribution location, many different distribution locations, and developing the control system requirements. Electric vehicle charging as a flexible resource that can contribute to the flexibility of the grid, and even the renewable generation itself as a flexible resource. One of the research areas that's very active is the development of what we call the smart inverter. for photovoltaics and for wind generation as well, but especially photovoltaics, where the inverter of the photovoltaics can help control the voltage so that we can put more PV on the same distribution system than we could if we just operate at a fixed power factor of unity, or even a lagging power factor, which is a little bit better. So these are some of the challenges that we face. Another issue that is making the penetration of distributed generation on the system grow at a faster rate, not necessarily PV, but other kinds of distributed generation, in the US especially, is the cost of natural gas. Natural gas prices are staying at a very low price, means that this is the levelized cost of energy over the lifetime of that resource, and it's in the cost per kilowatt hour. And we can see that if the price of natural gas, and this is for a commercial, a building size generation facility that would use natural gas, like a small gas turbine. And at the prices that we have now, between $4 and $6 per million BTUs, the levelized cost of energy for different technologies is in the range of 10 cents per kilowatt hour. That's less than those facilities pay for electricity in California. And that's why many of them are putting in their own generation. It's cheaper. It's cheaper for them to have their own generation. And if they feel like those gas prices will stay at those low levels for a long time, then it makes sense for them to have their own generation. And the utilities have to deal with that situation and figure out what that means for their business model in the future. The model works for even residential facilities, but it's more expensive per kilowatt hour for the technologies at the residential level, but it still can work. It's especially attractive if you can use the heat. So the combined heat and power locations are even more beneficial in terms of the economics. And even at 20 cents per kilowatt hour, we're still cheaper than electricity in Hawaii or in California, depending on what tier of the rate structure you're on. So we're seeing even residential applications for fuel cells. Companies like Bloom and others are offering technologies that take advantage of the price of natural gas. So this is something that becomes a technology that we have to deal with. If they're going to interconnect with the grid, then we have to deal with these distributed resources all over the grid. Another driver that's particularly important right now in the US and some other places in the world is, we use the term resiliency. We've used the term reliability for a long time, but now we have very good reliability. But we still have storms that come through and destroy parts of the system. And we have people that are out of power for a week or 10 days at a time. And we actually don't even count those events in the reliability statistics. So we calculate the reliability without those events. We throw them out because they're not representative of the normal operation of the grid. But they're very important events. So we have a new term called resiliency to deal with those kinds of events. And people are putting a lot of value on being able to deal with those events. So they're looking at their own generation, being able to ride through those events with their own resources. In the state of Connecticut, last week, they announced the award of 9 microgrid projects for critical facilities around Connecticut. So they could build local generation and storage and protect those facilities in case of a long duration outage. New Jersey, Massachusetts, other states looking at the same thing. The military bases in the United States are all looking at microgrids. So the technology of microgrids is gathering a lot of momentum, and it has some of the same requirements that we talk about with the digital grid, of having a controller that can supply power from local generation, or supply power from the grid, or supply power from storage devices, depending on the needs of the load and the economics of the different power sources. And resiliency being one of the drivers that's making these options economically viable. So we look at that. And I mentioned the control system challenge. To integrate these technologies means we have to be able to change the way we design the controls of the grid completely. If we're going to optimize the performance with all of these local generation sources with their own controllers, we need to rethink the distribution management system to take advantage of the intelligence that's at all of these distributed locations. So that's something that we continue to work on. And one of the ways that we work on all of these challenges is demonstrations. We work on the technologies along with the vendors and suppliers. So we work on new technologies to help make this work, new control system technologies, new energy storage technologies, new generation technologies, new load management or demand response technologies. And we define the information and communication system requirements for those technologies. And then we have to try them out together in demonstrations. And that's what we're trying to do in our smart grid demonstration initiative. We're in the 5th year of an initiative that involves 23 utilities from around the world. 15 of those utilities are doing large-scale demonstrations of integrating distributed resources. Some of them are integrating storage with photovoltaics, with demand response, so we can use loads to help balance those resources. Looking at commercial buildings that we can, in Con Edison in New York, taking advantage of the fact that commercial buildings already have backup power sources and optimizing the use of those energy resources to make sure we don't overload the distribution grid in Manhattan during the summer when it's very hot. I mentioned AEP and distributed storage, Duke Energy looking at distributed storage, but also electric vehicle charging infrastructure as a flexible resource. EDF in France integrating customer and resources throughout a whole town to help provide energy when there's high demand or when there's a problem on the transmission grid that provides a bottleneck and we need to reduce load. We can have all of the consumers in that town getting a signal and having local controllers like your home energy management systems to accomplish that load. So we're learning a lot from all these demonstrations. It's helping us with standards. It's helping us with understanding the costs and benefits of the different technologies. And it's helping us move the technology forward. The project involves a lot of coordination with different organizations. Standards organizations being particularly important. As we learn from the demonstrations, we want to take those learnings and make sure that the standards that we have for information exchanges, for communications, can deal with the realities of what the technologies can do and can't do. So the standards participation is particularly important, but also dealing with the different research consortiums around the world so that we're coordinating the lessons learned from all these demonstrations and taking advantage of it. And we work closely with the European smart grids people, as well as with the smart grid efforts and smart community efforts in Japan as well. So that's a very important part of these demonstrations. Along those lines, I wanted to mention the work of testing and evaluating where something like the digital grid concepts and the digital grid router in particular, which is the first technology that we tested associated with this. So some of the use cases that we think will be very valuable for this technology include integrating distributed generation. So we have all these generation sources. We need a controller that can take the local source along with the power from the grid and supply what's needed for the load. It's exactly what the digital grid router is designed to do. Energy storage is part of that equation. Having a port that can supply the DC to the battery and take the battery to supply the load so that the battery becomes a local resource integrated with the grid as part of the operation. So that's a use case that we want to look at very closely, integrating energy storage with local generation and supplying critical loads for resiliency. This is an application that has right now tremendous application in the US to have a controller that can supply critical loads, critical facilities, and optimize where the power is coming from to supply those facilities depending on the conditions on the grid, the prices of the electricity on the grid, the reliability of the electricity from the different sources. Voltage control is a very important application as well. Sometimes we don't think about that when we think about just supplying power from different sources, but we're actually working voltage control for energy efficiency is a big initiative in the United States right now. We call it conservation voltage reduction. We're working on managing the voltage on a distribution system to a much tighter level and actually reducing that voltage to the lower end of the allowable range, because a lot of loads work better there. They save energy, especially motors for like refrigerators and fans and air conditioning compressors. They all like the lower end of the voltage range. The magnetizing currents are lower, the losses are lower, and we save energy. We actually, one of the estimates are that if we reduce the voltage about 2% on residential feeders across the United States, that's about 47% of the feeders, the distribution systems, we could save approximately 2% of the energy in the whole country just by reducing the voltage. The customer doesn't have to do anything, just uses energy like he does normally. We reduce the voltage and we save 2% of the energy in the country. So it's very attractive. You can invest on it, modernizing the distribution system, and you get the benefit of you save energy. Unfortunately, our distribution systems are not really set up to manage the voltage that close. So technologies that can help us control the voltage for those loads, or when we reduce the voltage across the whole feeder, if that has a problem for some loads, we can put something like the digital grid router in front of those loads and manage the voltage to those specific loads to whatever they need. So this voltage control is a very active research area. Adding lots of photovoltaics on the distribution system just makes it even more complicated. We're trying to control the voltage to a very tight range, and now we got all of this photovoltaics with clouds going by that are causing the voltage to fluctuate all over the place. So we make the problem even more difficult. So now we need technologies that can control the voltage very quickly in response to changes in the photovoltaic generation and keep it within a tight range. So voltage control, very important research area. Incorporating electric charging, electric vehicle charging, very important area. It definitely is a use case that will be very important for the digital grid router. And demand response being part of with the communication and information interface to this device, we can interface with the home energy management system and the intelligence that might be in the appliances themselves to respond to signals from the grid and provide part of the flexibility that the grid needs. So it's a very exciting time to work on a technology like this, and we're excited about it as well. You can find information about this smart grid demonstration. This is the website for where we have a lot of public deliverables and presentations and case studies about the individual demonstrations that are in our smart grid demonstration initiative. And I wanted to mention a new demonstration initiative that we're just starting this year. It's another 5-year demonstration initiative, and the objective is to work on applications for all of the data that we're getting as part of the smart grid. When TEPCO finishes their advanced metering program by 2020, is that when it will be done? They'll have 27 million meters that are providing voltage, current, and power data every half hour. So every half hour we have 27 million readings of data. And then over a whole year, you can multiply that out. It's a lot of data. And there's a lot of things that can be done with that data that have value for the operation of the distribution system. In this area of voltage control, the data from those meters is very valuable. We can manage the voltage on the distribution system better by having that data from the meters. We can manage the transformer assets on the distribution system better by continually looking at the loading very accurately. We can provide services for the customer based on understanding their load profile and where they fit compared to other customers that are like them, to help them save energy and operate more efficiently. Lots of applications, lots of other sensors. We have sensors on the distribution system. We have phasor measurement units on the transmission system. We have geographic information systems. We might be using social media data from customers. We're working with a number of utilities during storm damage assessment to be able to process all of the pictures that customers are taking of poles that are down and lines that are down, and processing that to see if it's accurate and make conclusions about the condition of the grid before crews even go out to do damage assessment. So lots of data, lots of applications, and we want to demonstrate those applications around the world for a collaborative group of utilities. So that's a very exciting project that links to the whole ICT part of the smart grid that we've heard about this afternoon as well. So that's very exciting, and I wanted to close with mentioning that. So in summary, we see the smart grid challenges fitting into these 3 areas as we continue with our mission of research for reliable, affordable, and environmentally responsible electricity. What's facing us right now is the need for flexibility as we see all these renewables and changing characteristics of the grid. We need resiliency to deal with storms and reliability problems, and we need to be connected. We need the challenge of the communication infrastructure to make all this work together is particularly important. So we think those are 3 kind of key requirements for the smart grid that are going to be the focus of our research probably for the next 5 years or so. So with that, I thank you again for the opportunity to be here and look forward to collaborating in the future. Thank you.
それではだいぶ伸びておりまして、申し訳ございません。それでは最後に 東京大学理事副学長松本陽一郎より閉会のご挨拶をさせていただきます。松本先生、よろしくお願いいたします。
ご紹介いただきました松本でございます。研究担当の理事副学長をやっております。本日はデジタルグリッド総括寄付講座の設立記念シンポジウムにお集まりいただきましてありがとうございます。東京大学は先進的研究に加えまして、社会実装型の総合的な課題についても、3つのキャンパス、本郷、駒場、柏、いずれのキャンパスにおきまして、ある意味で横断的に連携して多様な研究成果を上げてまいりました。特に総括寄付講座は、総長直轄ということで、基本的に学内外のですね、横断的な活動をするということをミッションにしておりまして、現在5つの総括寄付講座が活動しております。デジタルグリッドはその中の一つということになります。電力ネットワークのイノベーションを実現するデジタルグリッド講座は、エネルギー・環境分野での革新的なビジネスプロセスに基づく社会変革を産官学が協力して、強力に実現していこうとするものでございまして、かなりの期待を集めているということは、今までのお話を伺われて、よくご理解いただけたかと思います。ソーシャルイノベーションに向けて、産業界とのコンソーシアムに加えまして、東大発ベンチャーと、ある意味で、まだ大きな企業体にはなって